Hi, I'm Timothy Lang from NASA Marshall. I am going to talk about a field campaign for which I served as the NASA project scientist. Next slide. Yeah, so the background for this field campaign, which was called Aloft, it's a really obnoxious triple nested acronym that I will get into the details of. But essentially, thunderstorms are known to produce these short duration, high energy pulses called terrestrial gamma ray flashes, and also longer duration emissions called glows. These are all related to relativistic processes created by the strong electric fields in a thunderstorm. TGS, we've kind of observed from just about everywhere, but glows are too weak to observe from space. They really must be observed from suborbital, either ground-based or some sort of aircraft or balloon or something like that. Because these things are transient and very seemingly rare, there is no real scientific consensus on how TGFs and glows relate to each other or to thunderstorm meteorology. The observations overall are pretty sparse. Your average gamma ray emission, like the gamma ray burst monitor that inadvertently detects these TGFs coming from the Earth, they might only see a few hundred a year. So there's really a pressing need to go direct to the storm and measure directly at the storm. And the best way to do that is using a high altitude aircraft. And so that's what the origin of a field campaign called Aloft is. Next slide. So, we wanted to observe TGFs and the relationship to gamma ray glows. And we wanted to perform spaceborne lighting sensor validation using improved instrumentation from suborbital platform. In addition to this, we wanted to look at evaluate new design concepts for the next generation of spaceborne lightning mappers. And just in general science, convection science, we wanted to make combined observations of microwave and lightning. Next slide. So the key to Aloft was the NASA ER2 platform. It's a high altitude aircraft that flies around 20 kilometers, so a little bit in the lower stratosphere there. But it gets over the tops of even some of the tallest thunderstorms on Earth, and that's really key. So we put the AR2 out, based it out at MacDill Air Force Base in Tampa, Florida, and from there we could reach many of the TGF hotspots, which are around Florida and Central America. That's the inset in this map. The main map is showing our different flight tracks for our 10 different science flights that we had. We also had a lot of ground-based lightning instrumentation. One of the unique aspects of Aloft is we had a near real-time downlink of gamma ray observations, and using that we could inform the pilot that we just went over a glowing region of a thunderstorm, and that could and so he would be empowered to immediately turn the aircraft around and refly that region. Next slide. Okay, so what did we use to detect the gamma rays? We had two different gamma ray scintillator instruments. The main one was the University of Bergen Bismuth Germanite, or UIB-BGO. Aloft was led in part by University of Bergen. It was very much a kind of a dual partnership between University of Bergen and NASA. Bergen built this instrument. It's similar to the instrument that flies on the Atmospheric Space Interaction Monitor on the space station. It has a mixture of BGO and LISO detectors, so it can detect both glows and TGFs, and it covers a fairly large dynamic range of particle energies with sub-microsecond sampling. The other instrument was iStorm, that's built by the Naval Research Laboratory. Very similar sampling, but slightly reduced dynamic range. Next slide. For lightning electric field, so Aloft is Airborne Lightning Observatory for FEGS and TGFs. That's where FEGS comes in here. That's the Fly's Eye Geostationary Lightning Mapper Simulator. GLM is an instrument on the GOES satellite that measures lightning over the Western Hemisphere. This detects lightning in 777 nanometer. And so that's what GLM does. And so FEGS does that as well because it's a simulator, airborne simulator. It's got a 5x5 array of these near-infrared radiometers pointing in all different directions to kind of map out the cloud top, what's going on optically. In addition, there's a few other just nadir-looking radiometers that, crucially, one of them looks at 337 nanometer, the UV channel. So 777 measures hot leader processes, and it allows you to detect lightning during day or night. 337 measures UV emissions from lightning streamers, which are cooler processes in the storm. And I also want to mention that 1600-meter shortwave IR nanometer channel was contributed by Sandia National Labs. And we also had a field change meter. That's a flat plate antenna that had fast and slow, but still we're looking like microsecond scale sampling. It's a very looking at broadband electric field changes. And we also had the lightning instrument package, which essentially measures the three-dimensional electric field near the aircraft. That's both the DC field, kind of like here's where the charge is, and the AC component, which is, okay, we're also detecting lightning. Next slide. We had 2 microwave radars on the aircraft, X-band, which is good at looking at deep convection, and W-band Doppler radar that's good at looking at cloud top processes. Both of these are, as I mentioned, Doppler, so you get information about updraft and downdrafts in the storm. Next slide. And then we also had passive microwaves. So this is, and we had a very unique combination of frequencies. There's no satellite that flies that has this kind of combination. This is everywhere. It goes all the way from 10 gigahertz, so X-band, all the way up into 684 gigahertz. That's looking at deep into the sub-millimeter. So you're looking at all types of ice and water particles in the cloud, water vapor profiling, all that kind of thing. So it's very unique and provides a very cool way of imaging the storm. Next slide. Okay, so we've got before I get into the summary of the results from the overall campaign, I did want to point out a notable case. This was a really intense mesoscale thunderstorm over Campeche Bay, Mexico, just off west of the Yucatan. This storm produced 83 observed TGFs or similar events, and at least hundreds of glows that we observed. To put this in context, like I said, the Fermi satellite might see 300-400 TGFs a year. So this in one storm produced, a very large fraction of that. And saw thousands of flashes, interesting behavior in the UV to IR in the flash optical emissions. We also observed transient luminous events from this storm, like blue starters, blue jets, and at least one gigantic jet. We also had multiple microwave satellite overpasses. And as you're watching the flight track over the storm there, that's the infrared from GOES, and on top of that is GLM flash extent. And as the aircraft kind of winds around over the storm, you see these little stars pop up, and those are the TGFs or TGF-like events. Next slide. So what do I mean by TGF-like event? So what I'm talking about here are these new discovery by Aloft. It's called the flickering gamma ray flash. This is a very rapid series of pulses in gamma rays that have no corresponding optical or radio signatures, as far as we can tell, or at least they're too weak to detect. But then once that gamma ray activity ceases, an event called a narrow bipolar event, which is a type of lightning flash, occurs, and then you have subsequent optical and radio activity. We believe these were probably observed by the original BATSI mission, which was the first mission to actually detect TGFs. But otherwise, people saw that but didn't know what to make of it. They knew it was from the Earth, but they just called it a TGF. But actually, it's probably a flickering gamma ray flash, and it was otherwise unknown before Aloft. Photoelectric feedback has just recently been posited as a possible explanation for this. Next slide. The other thing is, like, as you saw from that storm that I showed, we saw over 100 TGFs overall, the entire campaign over about 10 science flights and hundreds of glows over a range of thunderstorms. The glows were highly dynamic. They seemed to be very highly tied to thunderstorm life cycles. So you have a storm develops, produces very strong electric fields. These are accelerating electrons. You start to cause all these relativistic processes, which cause the glows. Embedded within the glows, you sometimes have these TGFs. And then the storm, an individual cell might die out, and then the electric field and the glows die out with it. But within a mesoscale storm, you have all these cells popping up like a boiling pot, and so this kind of glowing overall storm can persist for hours. Next slide. And as it turned out, it looks like using microwave observations really came in handy. We did some comparisons between the different sensors, and of course, glows are caused by really strong electric fields, but there's a certain wavelength at G-band, which normally we use just to profile atmospheric water vapor, but it turns out it provides almost a pure look at graupel in the upper parts of the storm. And where you have a lot of graupel, which is rimed ice, you have strong electric fields, and then that's why it's a good predictor of whether or not a storm is glowing. Next slide. Yeah, and then looking at the value of UV emissions versus the near IR for mapping lightning and detecting lightning, we showed that you could actually detect UV emissions during daytime, which we did not actually know for sure that you could do that prior to a loft. And you can see the value of this. On this particular case, we're showing a TGF that pops up, and then there's strong electric field changes associated with that. And then you see emission, optical emission, subsequent to the TGF that's only in the UV. You don't see, so there's only a streamer process here. There's no thermalized leader channel in the lightning. Next slide. Yeah, so some additional loft discoveries. Basically, we had a direct overpass of the ASIM instrument over that storm that I showed before. It saw no TGFs when we saw like a half a dozen TGFs. So those are all too weak to be detected from space. Follow-up modeling showed that probably almost all TGFs that we saw and the FGS that we saw were not detectable from space. So what this means is that the spaceborne TGF climatology is significantly underrepresenting thunderstorm gamma ray phenomenology. Next slide. So the loft was very successful, so we're going to do it again. This campaign is called Enlighten. It's going to happen in July of 2028 with ER2. It's going to be very similar to a loft, but the thing we're going to add here is we're going to add gamma ray imaging via pinhole camera and collimated detectors, as well as an airborne VHF interferometer for mapping out the lightning flash in the cloud. And the idea here is to understand where, not just did we see gamma rays, but where did they actually occur in the cloud? Because that is the main question we don't have answered at this point. And so that's what the goal of Enlighten is to do. Next slide. So Enlighten is funded and is going to happen. But there's a proposed campaign, which we're not sure yet if it'll happen, but it's called Declare. It's led by the U.S. Naval Research Laboratory. And basic gist of this is let's do a loft, but let's do it over the Mediterranean in the winter, where you also have some intense storms, but they're shallower. So it's another more interesting. It's a way of looking at differences in thunderstorm morphology and how that might affect gamma ray emissions. Next slide. And this is my final slide. You can see my conclusions here. The main thing I want to emphasize is that you could not do this from space. And it's really hard to do this from the ground because you kind of have to wait around for it to happen. You really have to do this with an aircraft. There might be a way to do this with a balloon. But you have to go to the storm. You have to be close to the storm to be able to detect the gamma rays because of the mean free path is very short for gamma rays in the Earth's atmosphere. And so suborbital is really the way to do this. And the ER2 really served us well for this project. And if you're interested, the data set is published. Thank you.